The process of normalizing a wave function is called normalization procedure. Where you multiply wave function with a constant n, so that it becomes n into psi. And then using normalization condition, find the value of n. Okay. Then n psi is the normalized wave function. Let's see one of the example. If your function psi is exponential I phi, where phi varies between 0 to 2 pi. So your minus infinity value is 0 and plus infinity value is 2 pi. So this is an unnormalized wave function. What will you do? You will multiply it with n. So n psi will be n into exponential I phi. And since it is a I value, so it's a complex function, so you will write n psi star will be n exponential minus I phi. And then what is the normalization condition? Normalization condition is psi 1 star d tau is equal to, is equal to 1. Is equal to 1 from minus infinity to plus infinity. So if you use these two, for psi 1 this one, for psi 1 star this one, and instead of d tau you write d phi, minus infinity is 0, plus infinity is 2 pi, then you can find out the value of n. So what you can write? You can write n, you can write n exponential I phi into n exponential minus I phi into d phi is equal to 1 from 0 to 2 pi. Okay. So you can write n square from 0 to 2 pi, and then you have e to the power I phi plus e to the power minus I phi, so e to the power 0 into d phi is equal to 1. This will give you n square from 0 to 2 pi and d phi is equal to 1, and integral will be n square. So what is n? N is 1 over root 2 pi. So we have found the value of n by using the normalization condition. So the normalized wave function now we will be psi will be equal to 1 over root 2 pi exponential I phi. This is called normalization procedure, and this is how we normalize the wave function obtained for a particular system, and this is a must. Okay. So normalization condition is very important, and you will have to do for every system this normalization. We will first find out the wave function and then we will normalize it. Okay. Another thing is that if a system has different energy levels, different quantum states, and it is represented, each of these quantum states are represented by a different wave functions. So psi 1, psi 2, psi 3, psi 4 are all different quantum states, each having a different energy. E1, E2, E3, E4, different energy. Then if each of these wave functions characterize a particular quantum state, then at a particular time the system could be in any one of the quantum state, either psi 1 or psi 2 or psi 3 or psi 4. So if we write the integral value from minus infinity to plus infinity as psi 1 psi 2 d tau, then this integral must be equal to 0, because at the same point of time the system cannot exist in two different quantum states simultaneously. Okay. So this we say is called orthogonality condition. Okay. The only thing is this, that here you have two different quantum state and here you have a 0 value if you compare with the normalization condition. So normalization condition is psi star d tau is equal to, or I will write psi n psi, write it again, psi n star d tau from minus infinity to plus infinity is equal to 1, or for a different quantum state psi m star d tau is equal to 1. But orthogonality condition is psi n psi m d tau is equal to 0 from minus infinity to plus infinity. Okay, and we can combine these two relationship as we say it's orthonormal condition. So we can write psi n psi m d tau is equal to delta nm. If I is equal to, if n is equal to, if n is equal to m, means both are same function from minus infinity to plus infinity, then we say delta nm is equal to 1. And if n is not equal to m, then delta nm is equal to 0. So this is your normalization, orthogonality. Okay. Now this condition is called orthonormal condition. Orthonormal condition. And if any wave function obeys this law, then we say it's orthonormal wave function. Okay. Once you have the wave function for a particular system, then we have to find out the physical variables for a particular system. Physical variable means position, momentum, linear momentum, angular momentum, x component of momentum, y component of momentum, everything you can determine. Okay. So, for finding out these, we have operators in quantum mechanics. So, operator formalism. Operators of quantum mechanics. We will talk about operators in the next class, but for the time being, I just wanted to tell you that this function we can write psi operated upon with a function psi, any operator you can write. This is an operator, and then d tau we can find out from minus infinity to plus infinity values. Okay. So, when you operate, this is an operator. With an operator, then there is another way of writing this thing like this one, psi n okay. This integral could be written in this form also, and this is called bracket notation, or in short we can write as n operator m also. Okay. So, it is very easy. If you have to write the normalization condition, then you write n is equal to 1 or m is equal to 1. If you have to write the orthogonality condition, then you write m is equal to 0, or for the time being psi m is equal to 0. Here you can write psi n. So, bracket notation is another way of writing the same integral, which we use as psi m or psi n d tau, or psi I j. You can write anything. Psi I j d tau is equal to delta I j. This delta I j or this delta nm is called Kronecker delta. Okay. So, finding out this integral is very important in quantum mechanics, because this gives you the physical interpretation, otherwise it does not give you any physical interpretation. Psi in itself has no physical significance, and if you have to find out this integral, then even from this integral is very important, operators. So, let us see. If you have a wave function for a system psi known, and it is a normalized wave function, and if you have to find out the position, then you will have to find out what is the operator of position. If you have to find the momentum, then the first thing which you will have to find out is what is the operator of momentum. So, suppose if I write this as an operator symbol, this as an operator symbol, then what you need to find out, if it is a normalized wave function, then you have to calculate the integral from minus infinity to plus infinity psi x psi dx. This will give you the position. Okay, it's very easy. So this integral you will have to find out for all the system. Now, what is this operator? Operators in quantum mechanics are mathematical symbols. for a mathematical operation. Each physical variable has a corresponding operator in quantum mechanics. Each physical variable has a corresponding operator in quantum mechanics. So, operators are normally given a symbol like this one or a symbol like this one, okay, cap or tilde. This is called tilde. This is how we represent an operator. So, if I write A cap in quantum mechanics, B tilde in quantum mechanics, it means they denote an operator. Okay, we will talk about the operator in quantum mechanics in details in the next class. Okay, that will be the second postulates. Till now, what I have done is the first postulates. Okay, first postulates of quantum mechanics I have done. A few examples of wave functions. Let me tell you. If I plot few wave functions, and will tell you how to do this one. Okay. Wave function psi versus x, I am considering it to be, and okay, all this is wave function of psi versus x, psi versus x, psi versus x. And if I say you have to find out which of these wave functions is acceptable wave functions, then you can easily point out that this is the acceptable wave functions. Okay. Why? Because here you have two values, not a single valued function, not continuous first derivative, slope changes very sharply, first derivative. Here also there is a break, not continuous function. Here also you will find for very small values of psi, you will have different values of x. So, but this is the only acceptable wave functions. Now, if you look at the Schrodinger wave equation, which is what? For a one-dimensional system. Okay. Now, we have a double differential equation. So, I said you that d psi by dx gives you the slope of the wave function. What will be ds square psi by dx square? It will be the curvature of the system, curvature of the wave functions. And curvature of the wave functions could be plotted like this one, a positive curvature, or this one like negative curvature. I'm just telling you that how qualitatively you can predict the shape of the wave functions. Okay. So if I write this as d square psi by dx square is equal to 8 pi square m by h square v minus e psi, then you can write, we can do this one. Okay. So this is a constant. You have v minus e psi is equal to d square psi by dx square, and this is what? This is a curvature. So for a positive value of psi, positive psi, if v is greater than e, then curvature is v is greater than e, so this part is also positive and this psi is positive, so curvature will be positive. If v is less than e, then this part will be negative and this part is positive, so it will be, curvature will be negative, so curvature is negative. For negative psi, if v is greater than e, but psi itself is negative and v is greater than e, this part becomes positive, so again curvature becomes negative. Okay. And if v is less than e, then curvature becomes positive. Okay. So you can have an idea about the shape of the wave functions qualitatively from the value of potential energy and total energy. This is total energy, not kinetic energy. Okay. So if you know the value of psi, that whether it's positive or negative, then you can get an idea about the shape of the wave function curve. Okay. Let's see. This we can draw a graph. We can make energy greater than V, energy less than V, and if you have psi greater than 0, psi less than 0, means psi is positive. Okay. So what should be the different shapes? It should be like, and again, so a positive curvature, a positive curvature, a negative curvature, a negative curvature. So a qualitative idea about the wave function, about the shape of the psi can be made simply by knowing the value of E, V and psi, whether psi is positive or negative and which value is greater, E is greater or V is greater, and which value is less. Okay. You can have a shape about that. This is all about the wave function part of today's lecture. Tomorrow we will talk about in the next class, operators in quantum mechanics.